more samples. You can also use the Aquatech 100, which is an autosampler that connects to the Stratum. It has a 100 position autosampler tray and 2 standard addition vials for internal standards or surrogate standards. Finally, last but not least, we have the Atomx, which is a multi-matrix autosampler prep system. And what that does is it combines the autosampler and the Purge and Trap concentrator into one unit, which can also handle soil extractions and can do dilutions, has 3 standard addition vials. Pretty exciting piece of equipment. But before we get into more detail about that, why do we need Purge and Trap concentration? First and foremost, it gives us an increase in sensitivity. So in particular, when we're looking at drinking water samples, some of our target compounds might be in really low concentrations, and we want to increase that concentration so that we get better sensitivity. Also, as many of you may know, GCs don't tolerate water very well. So if we put a lot of water onto the column, that's going to affect our detection later on down the road. And so by concentrating the volatile organics, we can reduce the amount of water that we have to introduce to the system. And then finally, we can ensure that we only introduce volatile organic compounds to the GC. So we don't put other contaminants that may be in our sample onto the column, which will obviously help with our sensitivity and our recovery. And with selection of traps, we can maybe even rule out certain organic compounds and focus in more on the ones in particular that we're interested in. So, how does all of that work? Purge and Trap works on an equilibrium theory. So we have a liquid sample with a gas headspace above it, and our volatile organics want to reach an equilibrium in concentration between that headspace and that liquid. In a static example, liquid being on the bottom here and the gas phase being on the top, our volatile organics will move out of the liquid solution into the headspace until they reach some type of equilibrium. Now, on highly concentrated samples, that may give us enough analyte in our gas to analyze. However, for lower concentration samples, we need to use what's known as dynamic headspace, in which we replace that gaseous headspace with fresh gas that has no targeted compound in it. And so what this does is it allows us to create a scenario where our system never comes to equilibrium. So as you can see, moving across these vials, as that headspace is continually replaced, more and more compound of interest comes out of solution into that headspace. And so that allows us to recover as much analyte as possible from our liquid sample. So when we're starting with very trace levels to begin with, this can be a real help. So that brings us to a basic Purge and Trap setup. And as you'll see here, in this case, our sample would be in the glass sparger here. Our gas would come in, our purge gas comes in, bubbles through, then it gets collected on the trap, and goes out the vent. After our purging period is over, this export valve would switch, and our carrier gas from our GC would then be brought in reverse order through the trap, and we'll get into that in a minute, why it needs to go in the back direction. From there to go back through the 6-port valve again and be carried through the heated transfer line to the GC for separation and detection. So that's a very simple overview, but how does that look in a real Purge and Trap concentrator? So here's a plumbing diagram for the Stratum, and what you'll see here is a couple things to note. The green lines are all the lines where our sample gas is going to come into contact in our purge gas. So in this case, we would have our liquid sample would be in the sparger. Our purge gas would come in, it would bubble through. It would be carried to our condensate trap first, which is a smaller inner trap that's kept at 40 degrees Celsius, so quite a bit cooler than the rest of the system. And what that allows is for the water vapor that's also purged, remembering that water likes to also seek an equilibrium between the gas phase and the liquid phase. So as you have that inert gas phase, water is going to volatilize and move into that as water vapor. So we need to remove that because, like we mentioned earlier, GCs don't handle water very well. So that's what our condensate trap does, is cools that sample and allows that water to come out as condensation. From there, it sweeps onto the analyte trap, where our compounds of interest are adsorbed, and then off to vent. But as we noticed, that was just for the purge and trap concentration. How do we get the sample into that sparger? So here's a diagram for our AT100. As you'll notice, everything works off of pressure, and up here we have a sample loop. So when we're filling that sample loop, we pressurize our vial with our purge gas, and the two-stage needle, liquid is forced into the sample loop, and then the excess goes to waste. So now, two things come up here. First, we need to choose a sample loop that corresponds to the sample volume that we want. And that's one of those parameters that we'll discuss later, and how that affects our purge and trap efficiency. But if we want a 5 ml sample, for instance, we would need a 5 ml sample loop. The other thing is the amount of time that we pressurize that sample. We need to make sure we do it for an adequate amount of time that we fill the loop, but as an extreme example, we wouldn't want to do it for so long that we pushed all of the liquid through the loop and then filled it with purge gas. And again, that's a very extreme example, but it's important that we time that pressure event to fill that loop adequately. From there, we then switch the flow of the pressurized gas to go back through the loop in the opposite direction, pushing the sample out and onto the concentrator. You'll notice here that the sample is swept through our standard addition manifold. And what happens here is these pressurized vials will inject standards much in the same way that an inkjet printer works. And so what that allows for is very accurate additions of standard in line with the sample, which gives no additional lines that need to be flushed or swept to make sure that all of that standard is entered into that sample. Plus, it's added before the concentration, before the purge stage, so that we can track our internal and surrogate standards through all the same conditions as our target analytes. So now that we've seen the two separate instruments that work in conjunction, let's put it all together for our Atomx. This is, on the surface, looks really complicated, but you'll notice that we still have a sparger, we still have our traps for concentration, and we still have our standard addition vials. So very similar, just combining the two systems. The big difference here, however, is that the Atomx has 3 standard addition vials, which increases the different options there for adding standards. For instance, you could set up a spike, matrix spike, in one of those. And then also we use a syringe here instead of a sample loop. And so what this allows us to do is switch between volumes from one sample to the next, and it gives us a more broad range of sample volumes that we can accurately measure. So if you want to go from 5 mils to, let's say, 7 mils, rather than having to make your own custom sample loop or switch sample loops, you simply program the software, tell it 7 mils instead of 5. It works very accurately, and then again, as you can see, the line sweeps through that standard addition manifold, so very accurate standard additions. Okay, so now that we understand some of the plumbing and how our sample gets from the vial that we collected it in to the concentrator, what are some of the things that are going to affect our purge efficiency? We have things like vapor pressure, temperature, solubility, and purge gas volume, and then we also have the method that we purge our sample. All of these things will affect our efficiency. So different compounds have different vapor pressures. Gases such as vinyl chloride or 1,3-butadiene have higher vapor pressures, and so they'll have higher purge efficiencies. They want to be in the gas phase more so than the liquid phase, so it's easier to get them to make that transition. Temperature also has an effect on our purge efficiency. So as you increase the temperature of the sample liquid, in this case it would be drinking water, you're going to increase the efficiency with which your VOCs move from liquid to gas phase. There's a drawback, there's a trade-off there, however, and that is that for each 10 degrees C rise in temperature, we're going to double the amount of water vapor that makes it to our trap. And so we need to really consider water management here, especially when trying to decide on a purge temperature. So as an example, for 1122 tetrachloroethane in water, we can see here various temperatures and purge efficiencies. And notice that in the first jump from 25 to 40, we get around a 50% increase in efficiency. However, for our next jump from 40 to 60, that increase in efficiency is more around like 10 or 12%. So what we can see here is an opportunity for method optimization, right? We don't necessarily want to just go for the highest temperature that our EPA method will allow, or the highest temperature that our concentrator can produce, because, again, for each 10 degrees C rise in temperature, we're doubling the amount of water we put on our trap, which is not good. And as we continue to increase temperatures, it's kind of a law of diminishing returns. We're not getting as big of an increase in efficiency. So what effect does solubility have on purge efficiency? Well, the more soluble a compound is in the matrix, in this case water, the harder it's going to be to purge. So as an example, methanol, which is very soluble in water, only has a purge efficiency of about 10%. And no matter how you change around those other parameters, such as temperature or purge gas volume, you're not going to see a major shift from that 10%. So what effect does purge volume have on purge efficiency? As we increase our purge volume, we will increase our purge efficiency. So in this case, 400 mils of gas is more effective than 200 mils of gas. It always will be. However, you can have too much of a good thing. And so by here, suggesting that as we increase our purge time, and again, the purge is a flow rate, a purge rate, so let's say 40 mils per minute over a certain time period. So increasing time increases total purge volume. Initially, as we increase, we're going to see an increase in response, right? We're going to remove more target analytes from the water and concentrate those on the trap. But at some point, we're going to exhaust our trap's capacity to hold, and that's going to be our breakthrough. So increasing our purge time beyond that point is just going to give us a nice flat response. We're not going to increase our sensitivity. We're not going to increase our total amount of target compounds that reach the GC through that range. And we can even reach a point where if we go for too long, we can start to push those compounds off of that trap, and we start to see a drop in response. So again, here's an opportunity for method optimization. We want to make sure that we stay somewhere in this front range where we haven't gone so far that we've reached a breakthrough, because anything beyond that is simply a waste of purge gas and a waste of time. It makes your sample prep take longer, which makes your analysis take longer, reduces the total number of samples that you can put through. So how about purge method? What effect does this have on our purge efficiency? Well, given the same volume of purge gas, how we introduce that gas to our sample is going to have an effect. If we introduce it as a dispersion of fine bubbles, there's going to be more surface area interaction between the gas and the liquid phase, and that's going to facilitate that transfer of material. However, sometimes we can't do that. For instance, if we do an in-vial purge, we have to use a needle sparger, which is going to release larger bubbles than a fritted glass sparger. Other cases may be more with wastewater, which doesn't necessarily apply to drinking water, but a dirty sample. If there's a lot of oil in the sample, or if there are particulates that can't be filtered out for one reason or another, they can actually clog the frits of the fritted sparger and either reduce that purge efficiency by making it more difficult for the gases to move through the frits, or they can contribute to contamination and carryover if we're unable to rinse those out between samples. So those might be two scenarios where you would want to use a fritless sparger. So maybe reducing your purge efficiency a little bit, but then improving other parts of your analysis. So now that we've talked about purging, how we get our sample out of the liquid phase and into the gaseous phase for introduction to our GC, we need to consider our sample band. So as we introduce compounds to our column, they're going to move through that column as a band. So to take, for example, vinyl chloride. If we put vinyl chloride in, if we're continuously purging it out of water and continuously sweeping that onto our column, we're going to have a long train of vinyl chloride, right? Because it's always coming in, it's always flowing through the column, always going into the detector. Well, that'd be a really long, wide sample band. We want smaller sample bands because if all of that compound of interest comes in as one blip, one spike, it's going to give us a greater signal-to-noise ratio and lower area-to-height ratios. And that translates to sharper peaks and better sensitivity and resolution. So we can't simply just purge these compounds out of water. We also need to trap them so that we can recondense that sample band and put everything in as one pulse. So we do that through trapping. So what are the requirements of a trap? A trap needs to do several things. It needs to retain our analytes of interest, but it needs to not retain things that we would consider a contaminant in this situation, such as oxygen, CO2, or water. So those need to be able to readily pass through the trap. Not only does a trap need to trap compounds, but it needs to be able to release those quickly and easily upon heating, which is the method that we use during desorb. Your trap needs to remain stable, so it cannot contribute volatile organic compounds to your sample. It should not serve as a catalyst for reactions between analytes of interest. It also should not react with your analytes of interest. It should be inert. And finally, it should be at a reasonable price. Because traps they're tools. We may switch them out for different analyses, and they do become exhausted at some point and need to be replaced. So here's a list of some of the more common adsorbents, and we'll get into some of these later. But I'd like to bring to your attention here that Tenax and Carbo traps are both good general all-purpose selections for drinking water analysis. And these are commonly referenced to and even recommended in EPA methods. So how is a trap designed? We use three-part adsorbent traps with the weakest adsorbent at the inlet of the trap, a stronger adsorbent in the middle, and the strongest adsorbent at the end. Now the reason it's set up this way is as our purge gas moves into the trap, all the different compounds that we're looking to measure are going to have different levels of adsorptivity, right? So we want our most strongly adsorbers, the ones that are really going to stick to that trap and be really difficult to release, we want those to get picked up by the weak adsorbents. And then things that are more difficult to adsorb are going to work their way through the weak adsorbent. They're not going to be stopped there. And they're going to catch on to either the stronger or the strongest adsorbent at the back end of the trap. And so what this allows for is that we have different types so that we not only ensure that we can catch everything, but we don't lose our weaker adsorbents because they get pushed off by stronger adsorbents and then go out to the vent. So this ensures that we can capture everything. And then during desorb, we reverse that flow, and we push everything back out through the same end that it came in. And again, the idea here is making sure that our really strong adsorbers don't come into contact with our really strong adsorbents. And so what that allows for is that not only do we get everything released so we can transfer as much compound to the GC as possible, but it also helps ensure that we don't get carryover of one sample to the next. So there's a lot of information here. This is a big table, but this, as well as the next table that I'm going to show, are both available on our website. Just go to the application notes section, and then search for Trap Selection Guide, and you'll find these tables. As you can see here, there's 11 different traps here. Lists what type of material they're made from, what kinds of compounds they'll trap, some of the different parameter restraints as far as temperatures and whether or not you can dry purge these traps. A lot of information there, but if we move on to the next one, we see that for specific EPA methods, in this case 524.2, which would apply to our drinking water discussion today, and then also 8260, which is a wastewater, pretty similar in the types and concentrations of compounds that we look at. We recommend a number 9 trap, but then you can see that you could also use a VOCarb or a number 10. And so as you can see, again, Tenax and VOCarbs are good general all-purpose traps for drinking water analysis. So now that we've talked about some of those critical parameters and how to choose them, let's move on to purge gas options. So what kind of gas are we going to use for our purging? Traditionally, we use helium. Helium is actually required for 524.2. However, some of the other methods, although they don't specifically mention nitrogen, will allow for it. You can use nitrogen. And both of these are more than adequate for purge and trap with our instruments, and that's because of our electronic mass flow controller. And what this does is it measures and controls the flow rate of the gas, not just simply the pressure of the gas in the system. And so by going to the software, you can select whether you're using helium or nitrogen, and it's calibrated for both. And so we can ensure accurate flow rates regardless of gas type. But which one works better? Well, we have a couple studies on that. So this will be the first application that I'm going to present today. We'll get into some data here. And this is a comparison between helium and nitrogen as purge gases. And so these are the parameters that we set up on the Atomx. And to note here is that we use the same parameters for both purge gases, the only difference being the type of gas. And you'll notice that there are yellow highlighted cells. These are the variables that we did not use. So in this study, we did not heat the sample above ambient, and we did not do a methanol rinse of the pathways between samples. But what we did use is, you'll notice we have a 2-minute desorb time, and if we come down here, we have an 11-minute purge time at 40 mils per minute. So here's the data. The blue line is the helium purge, the red is the nitrogen purge, and we're looking at TICs, or total ion chromatograms. And if you look at the table, you'll see that our RSD on the nitrogen purge and then the helium is 10 and 8.3 respectively, so very good RSDs. Our average MDL concentration for nitrogen and helium purge was 0.32 and 0.33 respectively, so the same. And the average compound response is 0.6 and 0.7 respectively. And again, very, very similar. And if we look at the TIC, we see that the blue, we see a little above on some of the late eluters, some of the heavier compounds, and on some of the early ones, the gases. And so we may have a slight increased efficiency in purging of those compounds with helium. However, nitrogen is very comparable and works really well in this scenario. And so especially at a cheaper price, may be a switch that labs want to consider. How do some of the other purge method parameters affect our recovery? So in this case, we're looking at purge gas volume. How does that affect our sensitivity and our recovery of our compounds? So on the left here, we have the Stratum purge and trap concentrator settings that we used with a 440 mil purge volume. So again, that 11-minute purge time and 40 mils per minute flow rate. And then on the right, we have a 350 mil purge volume. And so here we did a 70 mil per minute flow for 5 minutes. Otherwise, you see all the other, we used similar parameters with the exception of desorb time. We had a 1-minute desorb time on the 440 mil volume, and we had a 30-second desorb time on the 350 mil volume. All other temperatures and parameters were held the same. As we see here, if we look at the results, column 1 and column 4 are our quadratic calibration results for the two volumes of purge gas, and we see very similar 1 or nearly 1 R-squares for the quadratic calibrations. So they both calibrate really well. Our precision as measured by percent recovery is also very similar, between 87 and 107% for the compounds listed here. And then you'll see that the accuracy is really good for both, with RSDs well into the single digits. And then if we overlay the chromatograms, the blue being the 440 mil purge volume in 1-minute desorb, the red being the 350 mil purge volume in 30-second desorb, we see that again, we have very similar results. The blue is slightly taller, so we get slightly better recovery on the larger purge volume. However, you'll also notice down here in the gases, we have a high water background here early on. So again, with increased purge volume, we've increased the amount of water that's made it to the trap. And then from there, we've increased the amount of water that's made it onto the column into the detector. So if the gases in particular, some of these early eluters, are of high importance you may want to consider reducing your purge volume or doing something else to help control your water, because you don't want that decrease in sensitivity. So this moves us into possibilities for EPA method 524.4, which is a proposed method at this point. I don't believe it's actually been implemented yet. But what this method proposes doing is officially allowing nitrogen, mentioning it specifically within the method, but also opening up some of the other purge parameters, specifically the recommendations on purge volume, purge time, and dry purge volume and time. So what we wanted to do here was see if we could use nitrogen as a purge gas, and then if we could optimize some of these other purge parameters. And so if we look at an example of a 20 ppb standard, we see that we get excellent recoveries, nice sharp peaks, and if we look at the extracted chromatograms for the gases, we also see that they're sharp peaks and we have good separation. And so this shows that as method parameters are opened up, we have excellent opportunities for method optimization. So now that we've talked about all the different options and parameters that we can choose on the purge and trap concentration side, how do we get that sample from our concentrator to our GC? First, let me start by stating that you should always refer to your GC manufacturer's specifications for your install. But we will cover a couple different options here. We have a splitless injector option where you cut directly into the carrier gas line. We can do a direct on-column connection. There are also volatile inlets available from several GC manufacturers. And last but not least, we have cryofocusers. So we prefer a splitless injection introduction when possible. And this is where the purge and trap system is hooked into series, if you look over here, with our injection port. So here's our carrier gas line. We cut into it, and we connect the transfer line using unions. Now we like this because it still allows for direct injections on the GC, which can be really helpful in method development and troubleshooting. It gives the ability to run splits. We like high splits between 60 and 100 to 1. However, you can still run splitless mode for sub-ppb levels if that's where you're looking. However, you're going to see more problems with water, and you're going to need longer desorb times if you do that. And then finally, you can run programmable split rates when using a splitless injector. The other option is direct on-column. And what you see here is we'll need an external pressure regulator to regulate our carrier gas from the tank into the transfer line, and then it goes into the injection, or directly onto the column. So what we have here is we don't have a splitability because we're putting everything directly onto the column, and because we can't split to vent off some of that water vapor, that's going to lead to water concerns, and we're going to need longer desorb times to make sure we move everything onto the column. Finally, we also have volatile inlets, which can be available from GC manufacturers. They do not give the ability for direct injection, so you lose that as a troubleshooting tool. And they can sometimes have issues with leaky connections. Finally, we have cryofocusers, and the way this works is the transfer line comes in, the sample is run past this cryofocus trap, and what that does is uses liquid nitrogen to cool that sample, which condenses all the analytes of interest and brings that focus back, tightens up that sample band, then heats it up and moves it into the GC. Typically used with megabore columns. It's not necessary, really required so much anymore. The fragrance analysis, people still use it, but they tend to lead to water issues because you then condense that water vapor and move that to the column, and you also have large consumptions of liquid nitrogen. So now that we've gotten our sample from our concentrator to our GC, what are we going to separate it with? Well, we prefer helium as a carrier gas as opposed to hydrogen because helium is more inert, hydrogen is reactive, and we see better results with helium. However, we have done extensive work with hydrogen, and I'll present some of that here in just a minute. And so each GCMS is going to have its own challenges with hydrogen. Some of the big ones we've seen are BFB tuning. You need to take special considerations for passing BFB tune. There are scrubbing effects. Hydrogen will strip contaminants out of your stainless steel lines, and so we find that there's a certain amount of break-in time to strip all of those compounds out. And then there are also mass spectral challenges as well. There can be some reactions that occur. Things can be collected onto the mass spec, especially these contaminants that are pulled out of the stainless steel tubing. It's all then transferred to your mass spec. Okay. So let's look at a comparison between helium and hydrogen as a carrier gas. Here are the Atomx Purge and Trap parameters. Again, the yellow cells are the parameters that we did not use, so we did not heat this sample and we did not do a methanol rinse between samples. But everything's the same here for the two, the difference in this study being the helium carrier gas versus the hydrogen carrier gas. And if we look at chromatograms for hydrogen, we see that we get nice responses on the 10 ppb standard, good separation, good sharp peaks, and that holds true also when we extract the ions for the gases. We have excellent separation between them and we have nice sharp peaks. The problems we ran into were on the BFB tune end with hydrogen. We typically failed on the 95 to 96 ion ratio, which can be a particularly difficult one to adjust because those masses are so close together. We found that lowering the column flow does help improve BFB tune. So what's happening there is you're putting less hydrogen into the mass spec with that lower flow rate. However, if you get too low on your flow rate, then you start to have separation issues and you start to see effects on your chromatography. So if your lab is considering switching to hydrogen as a carrier, BFB tunes are something you're going to need to address. And just make sure that you have a good plan for how you're going to tune your mass spec so that you continue to pass BFB. So what are some column considerations? We prefer using 20 to 30 meter columns in the 0.18 to 0.25 bore size. And what that does is gives us shorter run times, which leads to faster sample turnover rates. We also like high split ratios, like I mentioned earlier, between 60 and 100 to 1. And then column phases are typically selected based on the method that you're running. So EPA methods will often recommend or even require certain phases here. And if you're not using an EPA method, choose your column phases based on recommendations for the analytes of interest that you're looking for. And most catalogs will give excellent descriptions of which analytes are retained by which phases. So finally, this brings us into purge and trap tips and troubleshooting. Here I'm going to cover some of the routine maintenance that you'll need to do with your system, how to use the sample history logs as a diagnostic tool. We'll cover different chromatography issues that you may be seeing and how to address those. Then we'll end with internal standard recovery variabilities and how to do system leak checks. So here's a copy of the preventative maintenance chart. You'll find this in the back of the user's manual for each concentrator that we sell. And you'll find that on a daily basis, it's a good thing to check your tank pressure to make sure you have at least 500 psi of purge gas in your tank, and make sure that your regulator is regulating out 50 to 100 psi. That's the operating range of the Stratum and the Atomx, and you want to make sure your concentrator is receiving at least that much purge gas. You also want to make sure that you empty your waste container as it becomes full. We don't like spills and messes. And just as importantly, if not more importantly, make sure that your DI water supply is full. The instrument uses DI to rinse the sample pathways, and you can also do a DI blank where the concentrator or the autosampler will pull from its reservoir rather than a vial that you put on the autosampler rack. It's recommended that you do daily leak checks, and we'll get into that in the software at the end on how to do that specifically. But it's a great way to catch problems before they exist, so that you don't have to go back and rerun samples after you discover that you had poor chromatography based on a leak. For weekly maintenance items, in addition to doing your daily maintenance, you also want to check your purge pressure stability, and we'll discuss that in a minute when looking at your sample history logs. And then finally, on a monthly basis, in addition to your daily and weekly maintenance items, you also want to inspect your glassware for cracks, chips, residues, contamination, and either clean or replace those as necessary. And that'll most likely cover all the typical issues you're going to see on a routine preventative maintenance side of things. So this brings us to our sample history log, and you simply, when you pull that up, you're going to see a list of all the samples that you've run. And I apologize that the font here is kind of small, but if you'll notice, the highlighted sample has a purge pressure of 4.5 psi. Now, that's pretty typical, and if you look through some of these other samples, we'll see a 4.7, we have another 4.5, we have a 4.6. This is nice and consistent. If you start looking at these sample pressures and you see that they're increasing as time goes, that's a sign that your trap is starting to break down and starting to reach the end of its lifespan. And so you don't want to let it go to the point where the instrument actually gives you a pressure failure, where the pressure has gone too high. So you just want to keep an eye on that, and as it starts to increase, that's a sign that you need to replace your trap. Now, if you're having problems with chromatography, or you're seeing peaks that shouldn't be there are peaks that are gone altogether, or you're having a lot of shifts in retention times, those types of issues, we want to figure out where they're coming from. Where's the root cause of our problem? And the way we do this is we separate our system into 4 entities. We have the Autosampler here on the left. In the middle, we have our Purge and Trap concentrator. Next to that, we would have the mass spec, and then finally the GC. And so we want to troubleshoot each one of these parts separately and rule it out as the cause of our issue. So how do we eliminate the GCMS? Well, if we've used a split-splitless injector connection where we've cut directly into the carrier gas line, we don't even need to disconnect our Purge and Trap. We can just simply confirm that we have a normal operation of the mass spec, and we can do that by doing an auto-tune, checking to make sure that we have adequate vacuum, and maybe cleaning the source. If we have a dirty source, we can clean it, put it back together, see if we're getting better results. If that's not the problem, or if we still see the problem after doing those steps, we move on to our GC. We can do a direct injection of our standard and see if our recoveries are consistent between injections, or if we get better recoveries than we did with the Purge and Trap system. And so that can confirm that we're not having issues on the GC side. If you're still seeing the problem, you can change out your injection liner and your septum, or clip your column. If you still see a problem after taking these corrective actions, then most likely it's not in your GC or your MS. So we've eliminated those two, and now we can move on to our Purge and Trap concentrator, and we can move on to our Autosampler. So how do we eliminate our Purge and Trap? So again, let me stress, this is after we've confirmed normal operation of the GC and MS. Then we can move on and confirm that our Purge and Trap concentrator is functioning properly. And we do this by running a diagnostics check. So you go to Tools, you'll find a benchmark within our software, and what this does is it will step you step by step through all the temperature heaters, through all the valves, through every piece of the instrument that has to move or do something. It'll test it and give you an output as whether it passed or not. And so this is an absolutely excellent tool for honing in on where a problem actually exists. So if you have a bad valve somewhere in that instrument, it's going to step through and check each valve, and it's going to identify this valve in particular is not working, rather than simply saying there's a valve issue or there's a leak issue. If you're having a problem with one of your heaters not actually coming up to temperature, this is going to identify which heater that is. So it's an excellent, powerful tool. If you don't find any physical issues with the Purge and Trap system there, then we can move on to making a manual sample load into the Purge and Trap sparge vessel, where we would manually introduce the sample, and this is going to eliminate our Autosampler. So if we see a problem when we load the sample in to the sparge vessel manually, then we know that it's not the Autosampler. However, if we load it in manually and we see good results, then we know that there's something going on inside of the Autosampler, whether we're not getting a consistent sample volume, or if we have an active site that's reacting with some of our analytes of interest before they make it to the sparger. So in the back of the manuals for each of our concentrators, you're going to find really nice flow diagrams that are going to help you walk through these types of things. So for example here, we would make a direct injection on the GC, And if we don't see a response, we don't see the peaks we're looking for, then we know we have a GC issue, and you refer to the GC manufacturer's manual on how to deal with that. If we do see a response, then it steps us through how to check our purge and trap system and make sure everything's working correctly. And as you work your way down, it'll eventually get you to a point where either things are working fine, or it'll tell you that you simply need to replace this part or the other, or it'll tell you that you've reached a problem where you're going to need customer service support, something that's just a little too difficult for you to tackle on your end. But this is also a very good tool for helping you work your way through step by step on analyzing your issue and trying to locate it. If we're seeing carryover or contamination, so you run a blank after a sample and you see something there, ask yourself a couple questions here. Are we seeing a carryover of the full target list, or are we just seeing a carryover of some of the late eluters, early eluters, or are we seeing contamination, things that aren't even in our sample list, things that we're not actually looking for? Once you identify that, it's going to help you understand where your source of contamination might be coming from. Next, we can do a GC run only, where we simply start the GC, run it, see what we get. If we still see that contamination come through, then it's likely contamination is trapped on your column. If we don't see any issues there, we can do a desorb only, where we step through all of the purge and trap parameters until we get to desorb. We desorb the trap, and we analyze that. If we see the peaks come out again, we see that contamination again, it tells us that our trap is contaminated, that we're getting carryover from one sample to the next within the trap. So if that happens, then we want to check our temperatures of our desorb and our bake, make sure they're both high enough to drive everything off initially in the desorb, and then make sure our bake out is high enough to remove anything else that's left over after desorb, to make sure that we start with a perfectly clean trap for the next analysis. If our issues aren't coming from either of those two locations, but we're still getting carryover and contamination, then we need to look at doing either a hot water rinse or a methanol rinse of our sample pathways to make sure we're not carrying over contamination from a high concentration sample, for instance, into our blank. If we're seeing carryover of other issues with early elution groups, in this case it would be missing peaks. On the GC side, we'd want to look at our split flow and see if we're having a leak, so we're not getting the split that we think we're getting. We might also be having column issues, where things are being either retained or allowed to go through too quickly, and they're missing their scan times. On the purge and trap side, we may have a leak, just a small leak that's allowing some of those lighter compounds to escape. We might have too much water coming into the system. We've already discussed how that water peak at the front end can really swamp out some of our gases if we're putting too much water onto the column. Could also be a sign of dry purge time that's too long. So we're running gas through that column for too long, or through that trap, excuse me, and we're eventually pushing off our early eluters. They're desorbing and they're going off the vent in that dry purge flow. Or we could be keeping our trap at too high of a temperature during the trapping stage so that they're never being adsorbed in the first place. They're just blowing through. And that might be a sign of a faulty heater, or it could simply be an error in your method that you have it set too high and you want to try reducing that temperature. Issues with middle eluters are very rare, but that can be a sign of the column phase going bad, so you might try a new column. On the purge and trap side, that can be signs of desorb preheat problems. It can also suggest that the condensate trap has too much water in it, or that the mass flow controller is leaking, so we're not getting the flow rate of purge gas that we thought we were getting. It can also be a sign of a bad trap, so we're not retaining these middle eluters as we purge. And then finally, issues with late elution groups. On the GCMS side, it could be a sign that you need to do some source maintenance. You might have a dirty source. Or it could be that you have your carrier gas flow set too low. Again, these late eluters are heavier, so it takes more flow to keep them moving through the column. On the purge and trap side, it could be a sign of poor purge efficiency. So maybe we have some restrictive sample tubing. We might have dirty glassware, so they're getting hung up in maybe like an oil slick that's on the side of the glassware, and they're not being purged in the first place. Sample might not be heated properly. These heavier eluters have higher boiling points, so they need to be warmed up a little more to get them activated and moved out of the liquid into the gas phase. Or we might have a plugged vent valve. In this case, we're purging, but we're not really flowing through the trap because there's no way for that purge gas to escape out the vent on the other side. And again, it might simply be a sign of a bad trap, a trap that's been exhausted and is no longer retaining the compounds that it's supposed to. If we're seeing water interference, on the mass spec side, it could be a vacuum issue. Maybe we're not vacuuming down to a low enough vacuum to remove all of the water that's in the mass spec. With GCs, you might try increasing your split flow to blow more of that water vapor out and not introduce it to the column. It could also be a sign of a bad column. On the purge and trap side, the condensate settings might not be optimized, or they may be failing outright. You may have water collecting in that condensate trap that's not being baked out between samples. We may not have a long enough dry purge time or a high enough dry purge flow to help additionally dry those analytes that are trapped on the trap before sweeping them to the GC. And then we may have a desorb time that's set too high. So if we shorten that desorb time, we put less material onto the column, but along with that, less water. Finally, let's talk about some internal standard recovery issues. So on the purge and trap side of things, we can try to isolate it to an active site. So in that case, we might look at swapping out sample tubing, the condensate trap, or the analytical trap. So in this situation, we'd be talking about our internal standard being either adsorbed in a place where it's not supposed to be adsorbed or reacting with something it's not supposed to react with. If we don't see issues on the purge and trap side to rule out the autosampler, we can try hand spiking a vial. So take a standard, put your internal standard into it, run it through the whole system without injecting internal standard in, and see what your recovery is then. Do you get good recoveries or do you not? If you do, then that might be a sign that there are some tubing restrictions on getting that standard from the vial up to that injector manifold. Could also be a sign of a valve malfunction in the injector manifold or pressure problems. You may not be pressurizing that vial, so maybe it's not tight and it's leaking, so you're not pressurizing the vial. If you're having issues with linearity or reproducibility, there's a lot of things that could potentially be happening on the GCMS side, more than we can get into here. But you might look into source maintenance, vacuum problems, EPC failures. That could be a sign of a bad column. It could be a sign of your method needing some optimization, in particular with your temperature program of your oven, so making sure that you heat things high enough to make sure that everything moves out of the column onto the detector in the time frame that you're looking. And it could be a sign that your multiplier is going bad. On the purge and trap side, again, there's a lot here that could be going on. It could be a method optimization. Maybe we're not using enough purge gas. Maybe we're using too long of a dry purge time, things of that nature. The trap might be going bad. Look into replacing it. Drain valve may be leaking, so we're not getting as much sample to the sparge glassware as we think. We might be putting too much water in. We may have excessive water vapor in the system in general that's being carried over to the column of the GC. Our temperatures might not be reaching set points. We might be getting carryover from one sample to the next because we don't have adequate line sweeping with the heated water. Maybe we need a methanol rinse. And we might be having sample preparation errors. We might have a dirty standard vial that's bringing something into our sample that we didn't intend. We might have a headspace over your sample. Remember, those need to be headspace free. They shouldn't have any amount of gas with which to equilibrate until they're put into the sparge vessel. And then finally, it might simply be analyst variability, not producing standards accurately from one time to the next, or not measuring out accurate volumes of sample to run each calibration point. So last but certainly not least, this brings us to purge and trap system leaks. So how do we, if we know our system's operating well, we haven't had any problems, but we've replaced the trap, for instance, or we replaced the sparge vessel, and we want to make sure that we're leak tight, but we don't want to go through the entire benchmark process because we don't anticipate any issues with any other parts. Well, in this case, we can do the leak check through the software, and that's under Tools and Leak Check. And it will simply pressurize things like the trap, the sparge vessel, and check to see if there's any leaks. And you can choose the parameters here, so you can say how long you want that to pressurize. And what that is once it comes to pressure, how long should it be able to hold that pressure? So do you want it to hold for 2 minutes? Do you want it to hold for 5 minutes, 15, whatever? You can select that. Leak check flow. What kind of flow do you want to go in? And then finally, what kind of delta are you looking for? How much of a change in pressure is going to signify a leak for you? Is 1 psi going to signify a leak? Do you want it tighter? Are you worried about a half a psi? Or are you fine with 2 or 3? You can change those parameters as well. And then the screenshot on the right here shows that once it reaches pressure, in this case, it'll go up to 25 psi, and then it'll start holding. The 2 suggests that we're going to go for 2 minutes. We're 30 seconds in, and if it drops below that delta, it'll immediately stop and tell you that it's gone below that. If it holds it for the whole 2 minutes, it'll tell you how much it dropped. But if it's within the parameters that you've set, then you'll pass leak check. And so this can be a really super handy tool for after you change out a trap or if you change your glassware. And then finally, just to go into a little more detail about the benchmark, you want to ideally run the leak check first so that you can make sure you rule those problems out, although the benchmark does do a leak check, I believe. And it'll check all your system controls, including solenoids, valves, heaters, flows, and that 6-port valve. And it'll make sure that there are no leaks in any of these things, that they're all functioning properly. And like I mentioned before, it's a very powerful tool that really helps you isolate in on a variety of potential issues. Thanks for listening to my talk, and with that, I will take any questions. I also want to point out real quickly that all of our application notes that I presented today, along with many, many others, are all available on our website, www.teledynetekmar.com. You create a free user login, and then you can download them for free.